All right, this is Mr. Smith here. This is section 5.2, evaluating and graphing polynomial functions. Okay. So we have been working with polynomial functions throughout this year. You just haven't known that. And so for the beginning part of the year, we talked briefly about these things. These are linear, and it could go either way, whether we call this a polynomial function, but for the sake of argument, we'll call it a polynomial function. Then we spent all of chapter 4 looking at these guys, which are polynomial functions, quadratic. And now the whole bottom's about to fall out, right? We're going to talk about now any degree polynomial bigger than quadratic, so cubics. Right, so a cubic polynomial, maybe y equals 3x cubed plus 2x plus 5. It's a cubic polynomial. We're going to look at maybe a fifth degree polynomial. Fifth degree polynomial. So at this point, any polynomial is fair game. Any polynomial is fair game. And so there's a few important pieces that I want to talk through definitionally. So number one, it's the biggest exponent that determines what kind of polynomial it is. Okay? So you look through all of the exponents and you find the biggest one attached with a variable, right? It's got to be x to the exponent. And that determines the degree, or that determines what type of polynomial it is. That's the first thing. The second thing, it should go in descending order. So the correct ordering says that if this is 5, then the next biggest exponent should come next. Notice here we skip one, but the next biggest exponent should always follow suit. It should be biggest on the left and then go in descending order to the right. Okay. The last thing is the term leading coefficient. First thing to note is leading coefficient does not mean the biggest coefficient. Leading coefficient is the number attached to the variable with the highest exponent. Okay, so we call this term the leading term, and the coefficient is called the leading coefficient. And I think we see that a little bit on the next slide. So this is just a general form of any polynomial. Okay, we can have x to the nth, where n has to be a positive integer. Okay, so we define a polynomial by saying n, the highest degree, must be a positive integer. Can't have negative integers to make this a polynomial, and you cannot have fraction or decimal values. And so we call this guy, again, the leading coefficient, and this whole thing is called the leading term. And when it comes to polynomials, the most important term is the leading term. Everything else outside here is not as important. Okay. The leading term is the key. All right, so here are some of the polynomials that we have spoken about thus far. Okay. So we've looked at constant functions, linear functions, and quadratics. And now we're going to start talking about anything down here, anything bigger. You can put this to your notes. I think the most important part is probably the terminology and what degree polynomial they refer to. I think I've used these terms enough that most of you are comfortable with them. But x squared, if I have an x squared polynomial, we call that quadratic. X cubed, we call that cubic. X to the fourth power, we call that a quartic polynomial. Okay. Again, notice the degree, descending degree. So this is x to the fourth, x cubed, x squared, x, and the constant term. Right? That is the proper formatting that you should write polynomials in. So you may say, what are we going to do with polynomial functions? The answer is, well, what have we done with the previous types of functions we've looked at? We've tried to solve equations. We've tried to graph. Those are exactly the same things that we're going to do here. Our goal is to be able to graph and solve equations. Now, of course, it's going to be a little bit more difficult because we're not just staying, and all of Chapter 4 was devoted to that level, right? Well, now we're not just staying at one level. And so you're going to have to keep track of a little bit more information, a few more examples. Okay. So here's a few functions. And the question is, which ones are polynomials, which ones are not? So if we look at this first one, x to the fourth minus 1/4 x squared plus 3. This is a polynomial. Okay. It has positive integer exponents. It is a polynomial. It's a fourth degree polynomial. Right? Fourth degree polynomial. And the leading coefficient is just 1. Right? Because there's an invisible 1 in front of the x to the fourth. Okay, so all we're doing is classifying right now polynomials. Example B. Notice I have an x to the first power. I have a constant, and I have an x squared term. This is also a polynomial. Now, it's a very ugly-looking polynomial. It's an ugly-looking polynomial. Again, the pi x squared term, that's the leading term. Why is that the leading term? Because x squared is the highest exponent for any variable. 2 is the highest exponent for any variable. And so pi is the leading coefficient. Now, you may say, well, Smith, we've never seen a quadratic equation with coefficients like this. It's true, you haven't. But if we were going to try to graph that, all of our rules about graphing would still apply. And if we were to try to use the quadratic formula to solve an equation like that, it would still work. It would just be very, very messy. Okay. Coming down here, I apologize, that should be a minus sign. So 5x squared plus 3x to the negative first power minus x. This function is not a polynomial. Okay. It is not a polynomial, and the reason is because of this negative 1 as the exponent. We're not allowed to have an exponent that is negative 1, any negative value. It's just not a polynomial. This function, just so you know, is called rational. That is a rational function. Okay. Likewise, this function, example D, is not a polynomial function because the variable is used as an exponent. Okay. That's not allowed in a polynomial, and this is called a power function. Okay. So these are different types of functions that are not polynomials. We will not study them in this section. We just lost minus signs here. Okay, it doesn't affect the problem. It just didn't copy when I put it onto the slide. So the original equation in part C was 5x squared plus 3x to the negative first minus x. And then here in part D we had x plus 2 to the x minus 0.6x to the fifth. One thing to note, even though there's an x squared term here, even though there's an x to the fifth term here, as long as one piece of it, it only takes one piece to make it not a function. Sorry, to make it not a polynomial. Let me say it again. It only takes one piece to not make this a polynomial. These are functions, it's just they're not polynomial functions. Okay? And so we will study them later, but not in Chapter 5. Good news for you. Okay? So, one of the basic things that we did with linear functions and quadratic functions is we plugged in a value. Right? We substituted in a value, and that's exactly what they want us to do here. That's exactly what they want us to do here. So they give us the function f of x, and they want us to plug in 3 in for x. So f of 3 equals 2 times 3 to the fourth power minus 5 times 3 cubed minus 4 times 3 plus 8. Literally, we just substitute in. And probably rely on a calculator. 3 to the fourth is 81 times 2 is 162 minus 3 cubed is 27. Remember, exponents first. We have to do the exponents first. And so if we work this whole thing out, what do we get? something like that, 38. I'm just pulling that from memory. Let's see. Official word is probably been easier just to do it. 23. Yeah. I apologize. Should have written 23 out there. Okay. And so this idea of how to plug in a number should form the basis for maybe graphing, right? If I want to graph a polynomial, I can make an XY table, and if I plug in 3, I get out 23. If I plug in 0, I get, let's see, 0, 0, 0, I just get 8, right? And so I can make an XY table just like we would make to graph a quadratic, except I would need a lot more data values. And the other piece of this is, if I were graphing a quadratic, I know that it's in the shape of a parabola, right? I know it's in that U shape, which is really, really useful. But I don't know what shape a quartic function is in. And so we need to study that a little bit. And what we call that is, we refer to it as end behavior. And end behavior is probably the most important idea in this section. Okay, it's very big. It's pervasive as we press on towards more advanced mathematics. Okay, so end behavior, understanding how the tips of the graph, right, how those last arrows, as we get really, really small x values, what the graph does, and as we get really, really big x values, how the graph behaves. And that will help us in our graphing pursuit. It won't tell us what's in the middle of the graph. Right, so we'll have to use an XY table to help us understand the middle of the graph, but it will help us understand the ends of the graph. Okay, and so here is our explanation of end behavior. Okay. And basically, if we have a graph, we're looking at, as I go really far off this way, I keep looking at x values that are getting bigger. And we say that by saying, as x goes to infinity. Okay, we use the arrow to represent the word goes. Okay, so as x goes to infinity, what happens to the y values? Do the y values get bigger, or do the y values get smaller? Okay, the y values go off to infinity, or the y values go off to negative infinity. There's only two choices, right, which is nice. And likewise, we can talk about, well, what happens when the graph goes off to this direction? We say that's as x goes to negative infinity. As x goes to negative infinity. Does the graph get really big? Do the y values go up, positive infinity? Or do the y values go down? Okay. And so again, there are only two options, which means there's only 4 total options for end behavior, which is nice. Makes it not too hard to memorize. But we're going to look at what happens as x goes to positive infinity, and what happens as x goes to negative infinity. And again, the arrow just means the word goes. You might want to put that in your margin, just because it's the first time, I think, that you've ever seen this notation. Okay. And so let me go to the next slide, where it kind of explains a little bit more. Okay. So if, and I'm actually going to start down here because we have a little bit more experience with even degreed functions. So if the degree of the function is even, like x squared, x to the 4th, x to the 12th, right? If the degree is even and the leading coefficient is positive, then the end behavior looks like this, where we get both ends pointing upwards. Okay? Ignore the middle part. The middle part here, we don't know what happens in here, so don't worry about that. I would tell you that you want to commit this to your notes. Yeah, all 4 of these, again, it's right in the textbook if you'd like that, but all 4 of these you want to commit. All right, so again, if the degree is even, and if you want to do the bottom first, that's fine, because I'll talk through the bottom. If the degree is even, what happens is x goes to positive infinity. As we go out this direction, what we see is the y values go up and up and up. So the y values go to positive infinity. Okay. Again, where it says f of x, you can replace that with a y. Okay. So as x gets bigger, as x goes to infinity, y goes to positive infinity. It's basically saying this arrow is going to be always pointing upwards. Likewise, as x goes to negative infinity, so as we're coming all the way this way, the y values also go to positive infinity. Okay? And the good news is you've already seen this, right? If I give you the graph y equals x squared, think about the end behavior of y equals x squared, right? So as x goes to positive infinity, we get the part of the parabola facing up here. As x goes to negative infinity, we get part of the parabola facing up as well. Okay, so we're talking about even degreed, positive leading coefficient. Okay. If we have an even degreed polynomial, again, x squared, x to the 6, whatever, but the leading coefficient is negative, now we get the flipped result, right? As x goes to positive infinity, the y values come down and down and down and down and down. Sorry. And as x goes to negative infinity, the y values come down and down and down and down. Okay? And we've seen this before, right? If I gave you the graph y equals negative x squared, right? How does that look? Well, it looks exactly like this, ignoring the middle part, because we don't know what's going to happen in the middle. So if we ignore the middle part, we're going to see a graph that looks remarkably like this, especially on a big scale. The idea of end behavior is it's supposed to give you a big picture understanding of what the graph would look like. Okay. The idea of end behavior will tell us a big picture idea of what the graph looks like. Okay. If we have an odd degree polynomial, x cubed, x to the 5th, x to the 7th, right? And the leading coefficient is positive, what we're going to see is as x goes to infinity, the y value goes to infinity, and as x goes to negative infinity, the y value goes to negative infinity. Okay. Again, we're not worrying about what happens in the middle. We're just worrying about the tails of the graph. Big picture. Okay, this is zoomed out, really, really far out. Likewise, if we have an odd degree polynomial, x cubed, x to the 5th, so forth, but the leading coefficient is negative. Now we kind of see the flipped of the last example. As x goes to infinity, y goes to negative infinity, so that gives us this tail. And as x goes to negative infinity, as we come in this way, then the y value goes to positive infinity. The idea of end behavior is a big picture idea, and it's very important. Also, this notation, I know some of you don't like this notation, but this notation is used over and over and over again as we go into more advanced mathematics. So you need to become comfortable with the notation itself. Okay. So there's more to section 5.2, but at this point I'm going to take a pause, and we'll end the video here, and we'll finish it up next time. So thanks for your attention. Have a good day.